What if I told you that a surgeon once used a 3D printer to save a child's life by printing a custom airway splint, something that literally could not have been made any other way? That's not science fiction. That happened. And it's just one example of why additive manufacturing might be the most important technology you've never fully understood. In the next 10 minutes, you're going to learn exactly what additive manufacturing is, how it actually works, where it came from, what makes it fundamentally different from traditional manufacturing, and why those differences matter more than most people realize. Whether you're a student, an engineer, or just someone who's curious about the future of making things, this video is for you. Let's get into it. Section 1. What is additive manufacturing? Let's start with the basics. Additive manufacturing, often called AM, is any process that builds a three-dimensional object by adding material layer by layer, guided by a digital design file. That's it. Build up, don't cut down. You've probably heard the term 3D printing. Additive manufacturing is the broader, more formal name for the same idea. 3D printing typically refers to desktop or consumer-level machines, while additive manufacturing covers everything from those home printers all the way up to industrial systems printing metal aircraft components. The process always starts with a digital model, usually a CAD file, which stands for Computer-Aided Design. That file gets sliced into hundreds or even thousands of thin horizontal layers by specialized software. The machine then reads those layers one at a time and deposits, fuses, or cures material to build the object from the bottom up. The material can be plastic, metal, ceramic, concrete, biological tissue, even chocolate. If you can figure out how to deposit it precisely and get it to stick together, additive manufacturing can use it. So here's something to sit with. If a machine can build almost any shape from almost any material, starting from just a file on a computer, what does that mean for how we design and make things? That question is exactly what the rest of this video is going to answer. Section 2. A brief history. Where did this come from? Most people think additive manufacturing is brand new. It's not. The first commercial 3D printing system was introduced in 1987. That's nearly 40 years ago. Charles Hull invented stereolithography, which we'll talk about more in a moment, and founded the company 3D Systems. His machine could take a digital design and build a physical prototype by curing liquid resin with an ultraviolet laser, one layer at a time. At the time, this was revolutionary because companies could create prototypes in days instead of weeks. Throughout the 1990s, several competing technologies emerged. Fused deposition modeling, developed by Scott Crump and commercialized by Stratasys, used melted plastic filament. Selective laser sintering, developed at the University of Texas, fused powder materials together using a laser. For most of its early history, additive manufacturing was used almost exclusively for prototyping. You'd design a part, print a prototype to check the fit and feel, then manufacture the actual part using traditional methods. Nobody was printing final, functional products. That changed in the 2000s and accelerated dramatically in the 2010s. Better materials, faster machines, and the expiration of key patents, which opened the market to new competitors, all came together. Suddenly, you could print parts strong enough and precise enough to actually use. So if additive manufacturing has been around since 1987, why is everyone talking about it now? Because the gap between what it could do and what industries actually needed finally closed, and we're still right at the beginning of what that means. Section 3. The 7 process categories. Not all additive manufacturing is the same. The industry standard, defined by ASTM International, breaks AM into 7 distinct process categories based on how material is deposited and bonded. First, vat photopolymerization. This is Hull's original stereolithography. A liquid photopolymer resin gets cured by a light source, layer by layer. Second, material jetting. Think of an inkjet printer, but instead of ink on paper, it jets droplets of material that are then cured with UV light. Third, binder jetting. A liquid binding agent is deposited onto a powder bed to glue layers together, used for sand casting molds and metal parts. Fourth, material extrusion. This is what most desktop 3D printers use. Thermoplastic filament gets melted and pushed through a nozzle, then cools and hardens. Fused deposition modeling is the most well-known version. Fifth, powder bed fusion. A laser or electron beam melts and fuses powder material. This is how you print strong metal parts for aerospace and medical implants. Sixth, directed energy deposition. A focused energy source melts material as it's being deposited, often used to repair or add features to existing metal parts. Seventh, sheet lamination. Thin sheets of material are bonded and cut layer by layer to form a 3D object. Each of these processes has trade-offs. Speed, cost, material options, precision, and surface quality all vary. Understanding which process fits which application is one of the most important skills in additive manufacturing. Here's the question that should be forming in your mind right now. If there are 7 different ways to do this, how does anyone choose the right one? That's where material science, engineering requirements, and economics all collide, and it's endlessly fascinating. Section 4. Additive versus subtractive manufacturing. Let's talk about what makes additive manufacturing genuinely different, not just in method, but in philosophy. Traditional manufacturing is mostly subtractive. You start with a block of material, metal, wood, plastic, and you cut, drill, grind, or mill away everything that isn't the part you want. It's effective, extremely precise, and has been refined over more than a century. But it wastes material, sometimes a lot of it. Additive manufacturing flips that equation. You start with nothing and add only what you need. Material waste drops dramatically. For expensive materials like titanium, this isn't just convenient, it's economically transformative. But the real difference isn't just about waste. It's about geometric freedom. Subtractive tools have to physically reach every surface they cut. That limits the shapes you can make. Additive manufacturing has almost no such limitation. You can print internal channels, lattice structures, and organic shapes that would be impossible to machine. There's also the question of customization. With subtractive manufacturing, custom parts are expensive because every new shape requires new tooling or new setups. With additive, you just change the file. The machine doesn't care if it prints the same part 1,000 times or 1,000 different parts. This is why additive manufacturing is transforming industries like aerospace, medicine, and defense, places where complex geometry, lightweight, and customization all matter intensely. And it raises a question worth thinking about. If you can make anything you can design, does that change how engineers think about design itself? Absolutely. And that's coming up next. Section 5. Design for additive manufacturing. Here's a concept that changes everything: design for additive manufacturing, or DFAM. It's the idea that additive manufacturing isn't just a new way to make old designs, it's an invitation to rethink design entirely. Traditional parts are designed with manufacturing constraints in mind. Straight walls, because that's what's easy to mill. Uniform thickness, because that's what's easy to cast. Those constraints became so embedded in engineering education that designers stopped questioning them. Additive manufacturing removes most of those constraints. You can now design a bracket that looks like a bone, thick where stress is high, thin where it isn't, with hollow chambers where no material is needed at all. This approach, often done with generative design software, can produce parts that are 40 to 70% lighter than their traditionally designed equivalents, with equal or greater strength. There's also the concept of part consolidation. A traditional assembly might have 30 separate components bolted together. With additive manufacturing, you can sometimes print the entire assembly as one single piece, eliminating fasteners, reducing assembly time, and removing potential failure points. The challenge is that engineers have to unlearn decades of design habits. It takes practice to think in terms of what's structurally necessary rather than what's easy to manufacture. But the payoff is enormous. Companies like GE have already printed jet engine fuel nozzles as single parts that used to be assembled from 20 separate pieces. The printed version is 25% lighter and 5 times more durable. That's not an incremental improvement. That's a complete rethinking of what's possible, and we're still early. As simulation software gets smarter and as engineers trained in DFAM move through industry, the parts being designed today may look primitive within a decade. Closing. So let's bring it all together. Additive manufacturing builds objects layer by layer from digital files. It's been developing since 1987, but only recently reached the performance levels industries need. It comes in 7 distinct process categories, each with different strengths. It fundamentally differs from subtractive manufacturing in material efficiency and geometric freedom. And when design philosophy catches up to the technology, the results can be extraordinary. We've only scratched the surface. In future videos, we'll go deep on specific processes, materials, quality control, and real-world applications across industries. If this video helped you understand additive manufacturing in a new way, hit the like button. It genuinely helps this channel reach more people who want to learn this stuff. Subscribe so you don't miss what's coming next. And drop a comment below with one question you still have about additive manufacturing. I read every single one, and your questions often become future videos. Thanks for watching. I'll see you in the next one.